higher order derivatives, doing the first, second, third, fourth, fifth derivatives, and so on and so forth. So here we have y, right? This is just some function in terms of x. That's called the zeroth derivative, by the way. It makes sense in some contexts to define the zeroth derivative, but it makes sense. We did the derivative 0 times, so there you go. The first derivative, we've already seen that. dy dx is f prime. We just use all our rules of differentiation. Right, chain rule, whatever. That's the first derivative. The second derivative, so the notation for it is this for Leibniz's notation. For Lagrange, it's just f2 prime. So this is the second derivative of y with respect to x. This is f2 prime. Why those 2's are in different places? It's because in calculus, this is the operator, right? Just like a plus and a minus sign are operator signs in arithmetic. In calculus, this is the operator sign. It tells you what you do to this input. So we do the derivative with respect to x to this function. When you do it twice, you're doing this operator 2 times. It's like almost like you're doing this operation 2 times to this function. So it's the second derivative of y with respect to x. So y is not squared because you're still doing it just to y, but the operator is squared because you're doing it 2 times. And it's actually really easy to find second derivatives. Use differentiate again. Right? 7 goes to 0. And then for the third derivative, now we're doing the derivative of y with respect to x 3 times. So the operator is cubed. For Lagrange's notation, it's f3 prime. And use differentiate again. And now for the fourth, there gets to a point when Lagrange's notation, you can't put like 4 primes, 5 primes, 6 primes. It gets ridiculous. So after a while, you just put the number of the derivative in parentheses. It has to be in parentheses. If it's not in parentheses, like this right here, means f of x to the 4th power. This means the 4th derivative of f of x. And then you just do that out. 72x minus 16 sine 2x. And you keep going. Right? So you just change the number in the parentheses, you change the number after the operator. So in general, the nth derivative is the nth derivative of y with respect to x. It's supposed to be n, which is f n to the x, and it equals whatever it equals. Every polynomial eventually differentiates to 0, but trig functions, exponential functions, log functions, those ones stay around. Let's do one example of this. Oops. There's my example. Let's find the second derivative of y for x squared plus y squared equals 9. This is implicit, which means we have to differentiate this thing implicitly 2 times, right? Because this means do the derivative not once, but twice. So first we differentiate once, 2x plus 2y dy dx equals 0. And then solve that for dy dx. 2's cancel out, as they are prone to do. And then we take this and we differentiate that again. dy dx differentiates to the second derivative. So dy dx differentiates to that. Negative x over y is the product rule. So the derivative of the numerator times the denominator minus the numerator times the derivative of the denominator over the bottom squared. This is the answer, but it's in terms of 3 variables. We have x, we have y, and we have dy dx. You always want to give your answer in as few variables as you can. And it's easy for us to get rid of this because we know what dy dx equals in terms of x and y. So since we want to use as few variables as possible, we do that substitution. So that's negative y plus x times dy dx. Right, and then we simplify that a little bit. But it's kind of bad form to have a fraction in your fraction. We don't want a fraction in our fraction. So we get rid of that by multiplying everything by the denominator of that fraction that we want to get rid of. So multiply the top by y and the bottom by y. That'll give us negative y squared. And then those cancel out, so it's just minus x squared over y cubed. And now we're good to go. Now we have the second derivative in terms of two variables. But we can go one step further and write this as negative 9 over y cubed. And how did that happen? Well, going back up to the original question, we were trying to find the second derivative of x squared plus y squared equals 9. Here, we have the opposite of that. We have negative y squared minus x squared, which is the opposite, so it equals negative 9. So we could substitute this whole thing out for negative 9. You see this happen a lot when you have nice and symmetric original functions. This is a symmetric graph, it's a circle, it's hard to beat that for symmetry. And a lot of times when that happens, the second derivative has that step where the original comes back into play. Okay.